Okay, so I think we are ready to start. So good afternoon to everyone and welcome to this 13th webinar on CCUS organized within the ECCSELERATE project. My name is Lorenza Piroddi and I'm a researcher at Sotacarbo. And today I'm going to be the chairman for this webinar, which is going to be about metering and monitoring technologies for CO2 transport. So first of all, let me ask all participants to keep their microphones and webcams turned off for the entire duration of the webinar. I also would like to remind you that questions are very, very welcome and that you can write them at any time in the question tab that you should be able to see on the right-hand side of your screen. Questions will be answered at the end of the webinar, so after the presentations. And I also kindly ask you to specify the presenter to which the question is addressed to. Finally, I would also like to remind you that this webinar is going to be recorded, so you will be able to find the video on the YouTube channel of ECCSEL. So before we start with the presentations, let me spend a couple of minutes to talk about the ECCSEL ERIC. ERIC stands for European Research Infrastructure Consortium and was born as a joint venture of 5 different countries, namely Norway, France, Italy, the UK, and the Netherlands, which provided open access to more than 80 world-class research facilities and infrastructure, which are located at more than 20 research centers. This was born with the goal of fight global warming and reduce CO2 emissions in the atmosphere by exchanging the knowledge about CCUS, so carbon capture, utilization, and storage. Within the ECCSEL ERIC consortium, we have the ECCSELERATE project, which was initiated in 2020, and it will end next month, so at the end of 2023. This ECCSELERATE project is funded by the European Union, and it has many goals. So for instance, increasing the use and long-term sustainable operation of the infrastructure within the ECCSEL ERIC, but also developing marketing, access, and services models for industry and also small and medium enterprises, increasing the international collaboration and expanding the national nodes, and also expand research from CCS to CCUS, so also including utilization, and maybe expand research also on an industrial level. In doing so, the ECCSELERATE project has a capacity building program with many activities inside. So one of these is, for instance, the series of webinars we are attending right now, but we also have specific workshops in summer schools and dedicated training courses. So coming to today's agenda, we are very glad today to host Yessica Arellano and Gabriele Chinello. Yessica is a research scientist at SINTEF, and she also leads the fiscal metering and thermodynamic task at the Norwegian Research Center for CCS, and she's going to be our first presenter. While Gabriele Chinello is our second presenter, and he's the head of CCUS at TÜV-SÜD National Engineering Laboratory. And he also is an external advisor for the UK Department of Energy Security and Net Zero. So I think without further ado, I will leave the floor to Yessica, who is our first presenter. So Yessica, the floor is all yours.
Thank you very much. I think you can see my screen.
Yes.
So thank you for having me. Thank you for having me. I will give a brief overview on the measurement landscape needs for CCS, which I hope serves as an introduction to the talk that Gabriele will give us. So I will start. Under typical CCS conditions, the most simplest way in which we can transport CCS, or the most simple value chain that we can expect to have, is a point-to-point transport, in which we will have a molecule of CO2 or a volume of CO2 that we will capture in a capture site, transport it, and store it in a reservoir. when doing so, these molecules of CO2 will undergo different phases depending on the transport mode that we choose, which is typically depending on the distance from the reservoir. So at the outlet of the capture site, we will most typically have gas phase, typically in not so high pressures. After increasing the pressure, we can transport it via pipelines, especially if we are transporting it onshore. For offshore injection or reservoirs that are farther away, we will typically need to increase the pressure further up. This will take us to a dense phase or to a liquid pressurized phase. And for even longer transport needs, we will have to ship the CO2, and this requires liquefaction of CO2 at lower temperatures. However, if we look at the volumes of CO2 that we will have to trade and to inject in order to meet the climate targets, we see that these source to sink models are not sustainable for upscaling CCS. What we are seeing is that from where we are now, which is practically no CCS projects injecting CO2, to where we need to be by 2050, which we're talking around 5 gigatons of CO2 stored per year, we will need an exponential increase of the CO2 traded and injected. And the implications of this is that the landscape for CCS will, of course, have to evolve in order to meet these needs. How we're seeing this evolution, in a way, of the way we are transporting CO2 and the way also that we do business, is that we will go from this source to sink model that I told you that it was the simplest way, into networks. We are already seeing industrial clusters coming together into what will be capture clusters to collect CO2 and transport it to the reservoir point via whatever of the means of transportation that I mentioned. Some of the interesting challenges of this type of CO2 networks is that, well, first of all, every capture process or every capture plant will have a different, or will result in a different composition that will depend on the source of the CO2 and the capture process itself. So what we expect to have is an assortment of different compositions in this network, but also these capture plants will most likely not operate 24/7. So this will give us a transient, not a transient effect, but more and more like a transient operation, where we will have variations in pressure, flow rate, and composition throughout the day or throughout the week. And this will be the new normal in the way we will operate CO2. If we look at the value chain of CCS, of course, from the CO2 perspective, from the fluid perspective, it is a one-way value chain where we capture the CO2, transport it, and inject it, and hopefully it will stay injected for a long time for it to be CCS and for it to be sustainable. But if we look into the business perspective, it's more of a two-way value chain, in the sense that it is not until the CO2 is actually injected that the capture site can claim credits, which will be the CO2 injected minus the amount of CO2 that is emitted during transport, if we were to choose shipping or truck transportation. So it is important to keep this in mind, because we will have to have an overview of the value chain that will we will need to think of the business in a bit of a different way, where we will have to have a complementary relationship of interdependence. We will, of course, need to have field measurements, as with any other process and any other business, of mass flow rate, because that's how we are trading CO2, we're trading it in mass. If we have volumetric flow rate, then we will need to know density, and this we can do either via equations of state, if we know the composition and the models are accurate enough, or measurement of the density, and then, of course, other variables like pressure, temperature, and composition. We also need to know, again, as we know the other process, the uncertainties with which we are measuring those quantities. We need to start thinking about data integration, because we will need to integrate data from multiple sources and from multiple variables. The way we look at the value chain, like I mentioned before, is also going to be slightly different from what we're used on other businesses. So we need to start thinking about corporate boundaries versus having this value chain overview that will be needed for pretty much all the parties that will interact in the value chain. And then the historic records, which for many processes are set what is the norm of the operations. When we have transient networks, then we might need to rely more on reference models. And this is something that I will just touch upon slightly on my next slide. So I come from a thermodynamics group here in SINTEF. So for us, of course, the thermophysical properties is at the core of our perspective, and I also believe it's at the core of the CCS transfer scheme, and this is when I want to elaborate a bit. So if we start with experiments, which is the most fundamental research we can do in this field, we will have we could have many outputs, but for the purpose of this, let's imagine that I have two outputs. One is the reference data, which is the most accurate data we could aim for. But this data is a true value, it's a reference value, but it is only true for the conditions at which it was taken, and it has certain uncertainty that it will depend on the lab and on the method. But this becomes the reference data moving forward, and it allows us to understand how the fluid behaves. Then we use this data for developing and tuning models. And what models do is that they allow us to actually use this data, because I have this kind of like this data that is in points, you know, pressure, temperature, and this is my reality or my reference data at those conditions. And with via models, I can interpolate between different sets of data and actually put this data to use. These reference models that we develop are then used for supervision, operation, and design. And it also allows us to do, if we are based on model, I will again talk a bit about this on my next slide, to have a bit of an idea if what we're measuring in the field is an actual representation of the physical phenomena, or if it's coming from faulty sensors. From experiments, we also get information that goes pretty much straight to operators, and this comes in the form of measuring accuracy and knowledge on the operational limits of the technologies that we are going to be deployed. And Gabriele will tell us more about that. So if we start, and then we close the loop in a way between modeling and operation, because the field measurements, both current and historic data, is also used in modeling for tuning the data. So if we look a bit more into understanding the fluid's behaviors based on these accurate experimental models or experimental data, this is some of the things that we need to know when we operate and that we get from this from these sources. The dotted line is we are all familiar with this. The dotted line is the phase the phase boundary between liquid and gas of pure CO₂, and the gray envelope that I'm showing is if we have 3% of nitrogen in that mixture. And what I want to highlight here is, of course, that we go from this straight line to an actual phase envelope, where I will have a range of compositions depending on where I am in the envelope. And if we were going to have, and of course, and different impurities will have a different effect. So what I want to show you here is that if those 3% were nitrogen, but were, for example, SO₂, not only the phase envelope is completely different, it's almost a line, it's very narrow, but it shifts the curve in a different direction. So it is important to understand how or what to expect from the fluid that I will be having in the field, depending on the composition that I will be having, which we know will vary depending on the time of the day and week, as I said. So if we look at just a simple example, and maybe I should try to get my pointer. Yes. So if we look at a simple example, at these conditions, 15 degrees Celsius, around 50 something bars, if I were transporting only CO2, I would expect to be in liquid phase. But if I have impurities, in this case, we are back to the 3% nitrogen scenario, I could be not only not in liquid phase, but I could be in fully gas phase. And to be able to actually get to the liquid phase is a difference of around 20 bars, which is not depreciable. If we look at this is the pressure composition or pressure versus CO2 fraction of this mixture. What we see, or not of this mixture, but at these conditions, at this temperature, 15 degrees Celsius, what we're seeing, for example, in this line that I'm showing is this condition here, this point in the middle of the phase. What we see there is two phases coexisting, a liquid phase and a gas phase. And what I want to highlight here is that, for example, the gas phase, a second phase that is formed in the pipe, will not have 3% nitrogen, will actually have something close to 8% nitrogen. And then I will have a liquid phase that will be enriched in CO2, going from 97 to, in this case, 98. So what I want to highlight here is that, yes, we need to know how the fluid behaves. We need to know how the phase envelope changes depending on the composition or on the impurities that we will have there. But we also need to understand how, if I'm operating in the second phase, how that second phase will look like. And in this case, the second phase is pretty much out of the specifications. So, and if we are thinking it's not nitrogen, if it's SO2 or SO3, then it has different implications for the integrity of my system. So all of this is data that we get from experiments. Now, we are also working a bit on understanding how we can deal with fault detection, how we can increase even further the reliability of our systems once they are installed in the value chain. So what I show here is just a roadmap for Internet of Things monitoring, and the QR code that you get there will take you to the paper. And there are two methods. There is a data-driven method that relies on vast amount of historic data in order to characterize the behavior of a system, but it doesn't require knowledge of the mathematical model because it doesn't rely on a mathematical model. But we do need to know what are the capabilities of the sensors that we are using in the field, and that this needs to be verified. Their accuracy needs to be verified for pretty much specific mixtures at which we will be operating. And we need, of course, have access to the historic data to, in a way, train this sensor fault detection based on data. And then we can also develop models. These model-based approaches have gained popularity because of the theoretical methods. They also have high accuracy and they are quite effective. But it is of the most utmost importance that we have models that actually are reliable and that have a lower accuracy, because with flow models that don't have the accuracy that we would need, then of course the model-based sensor fault detection will fall short. Now I will discuss a bit more about measurement in the field and accuracy and operating limits. I have already mentioned that there will be broad measurement needs throughout the value chain. We will for sure need mass flow measurement, not only to control our system, but every time we have a custody transfer in the value chain. We will necessarily need to know what is it that I'm transporting at different points in the value chain, at least whenever I have joining currents. I will need to know the density, either by measurement or by estimating it with equations of the state. And I need to know how much CO2 emissions are being released during transport. Depending on what is it that I need these measurements for, I will need different accuracies. And the most strict accuracies are those that involve money, fiscal metering. And of those, for example, the one for liquid is perhaps the most strict one that requires 1% accuracy per meter that is going to be installed in the field. But there are other regulations but other indications of how things might move forward in the future. The European taxonomy, which, as you know, sets guidelines to define what activities and what companies are sustainable, or yes, what activities within which companies are sustainable or not, requires that not more than 0.5% of the mass being transported could be leaked. So then that means that we need accuracies lower than that in order to be able to prove that we are complying with that figure, and then that our system or our process is sustainable. So there is this project that I lead. It's called Macon CCS, and as part of that project, what we tried was to match the measurement needs and different measurement technologies. So we started, and I will start filling up this table. So we started by looking into why is it that I need to measure? What is the purpose of my measurements? Is it because I need to comply with specifications? Is it because I need to ensure integrity on my system? Is it for ETS credits accounting? Is it for custody transfer? Is it because I need to ensure a mass balance throughout my value chain? Is it for process control? And then we looked into where in the value chain we will need to perform these actions. And you see them for every objective. We see where we will need to have some measurement points of certain characteristics. So capture sites, capture clusters, pipelines, shipping terminals, including terminals, injection, and temporal storage. And then we try to match that with what is the measurement? What is it that we're measuring? We will need to measure composition and water dew points. We will need to measure mass flow rates or volumetric flow rate plus density. And we need to measure level when we have storage. And we will need to identify if I have a second phase that could either impact the integrity of my equipment or could decrease the accuracy of the metering system that I have downstream. And then we matched in a way all of them. So I don't want to overwhelm you with all of this. Again, in the QR code is the preprint of this work. But just to show you a bit how it works, if we start with custody transfer, we will know that, and the double ticks mean that we will for sure need this. So we will for sure need custody transfer. For custody transfer purposes, we will need to know the composition of our stream, and we will need to know mass flow measurement. If we don't have mass flow measurement, but volumetric flow measurement, then we will need density. And some or most of the meters are quite sensitive to having a second phase. So then we will benefit from phase identification or second phase identification. So all of these subjects are things that we are working on. Some of the earliest movers or things that we're working on now to partially abate some of these obstacles are the ones that I highlight here. It is still a complex task in hand, so it involves international cooperation and a mixture of funding opportunities. So just to highlight some of the work that we're doing, we are developing a primary flow reference primary flow equipment and materials as part of, at a European level, as part of MedCCUS, which is a project funded by Euramet, and at a Norwegian level by Preference, funded by the Research Council. We are, SINTEF together with NEL, looking into opportunities for European large-scale metering facilities for liquid CO2, in this case. We are looking into developing monitoring tools. Again, as part of a European project, CoreEU, we are advancing state-of-the-art of measurement technologies, not only for fiscal metering, but to match this, this mesh of needs and challenges. And we're working on verification and validation of data from sensors in a project called Signify with NTNU. So, like I mentioned, there is still a lot of work to do. We need to advance the state of the art of the metering technologies. We need some type of overarching monitoring solution through the value chain to be able to do some sort of CO2 tracking. And not less important, we need innovative business models that involves evolution of the regulatory framework, development of standards, and best practices for transnational monitoring of CO2. So this is what I had to show you. Thank you very much.
Thank you very much, Yessica. The presentation was very, very interesting. I remind that we will have time for questions later at the end of the two presentations. So I think now we can leave the floor to the second presenter, who is going to be Gabriele.
Yes, good day, everyone. Can you see my screen?
Yes.
Yes. All right. Let me put in full mode, full screen. There we are. Okay. Yes. Thank you, Yessica, and thank you to the opportunity to be here presenting. So I'm going to present some of the test results we got so far on Coriolis meter with CO₂. So this presentation will be focused on Coriolis meter mainly. So first we start just with a very brief introduction of what TÜV-SÜD National Engineering Laboratory, then touching on calibration facilities, why they're important, how many they are there. Then some test results in gaseous phase, some test results in liquid and dense phase, and just future plans we have at the minute. So what is the National Engineering Laboratory? If you're not used to us, we are the designated institute for flow metrology in the UK. So we hold the UK national standard for flow measurement. We were a UK government research laboratory in the past and then privatized, now part of TÜV-SÜD. And yeah, our expertise is in flow measurement from many years, and we are also driving international standards at ISO and BSI level for flow measurement. We are part of the National Measuring System in the UK, along with the National Physical Laboratory and the other laboratory that you see here on the right-hand side of the slide. And we are funded by the Department for Science, Innovation and Technology. Just a feeling of some of the facility and their scale. So we go from large facility, from example, our advanced multi-phase facility on the right-hand side here, 33-meter long separator, up to 130 bar. And then we also have something smaller, like our mobile facility for hydrogen refueling stations, and many other facilities. So what about calibration facilities for CO₂? In this picture, you can see in the background, you can see our CO₂ gaseous calibration facility. That's nominally 8-inch. So as Yessica was saying, we will need to measure the mass of CO₂ along the CCUS chain for several reasons, as Yessica said. So we will need a metering skid at several locations, and we will need to ensure the quality of that measurement. So quality assurance will be a key aspect. One of important step in quality assurance is calibration and recalibration. So before installation and after installation during operation. So how do we do that? One option is to take out the flow meter and send to a calibration lab. So where are the calibration lab for gaseous CO₂? I've tried to put them in a slide, and apologies, this is based on my knowledge, my best knowledge. And so I identified 3 ISO 17025 accredited facilities, one in Canada, Fortis BC, one in the Netherlands, DNV, and one in actually TÜV-SÜD in the UK. And there is also another facility that is IFE in Oslo, Norway, which is nominally 2-inch, but to my knowledge is not accredited. I didn't include any facilities before 2-inch, but there are out there, you know, also at university level and so on. And I've tried to calculate the maximum flow rate in MTPA that they can calibrate at, just to give a feeling of the magnitude we can go with. So to be honest, for gaseous phase, you know, we can improve, but there is already something there, right? What about the liquid on dense phase? Well, that's another story. It's a bit more different, and is scarce facilities out there for calibration. Again, at IFE in Norway, a 2-inch facility that can go in liquid and dense phase. And the other one is the one we are building at TÜV-SÜD National Engineering Laboratory in the UK. But again, it will be a 2-inch facility. And the primary purpose is not really about calibrating big meters. It's about conducting the fundamental research for assessing the transferability of calibration between CO2 and other fluids like water. So, and that facility will be a primary standard facility, so a first of its kind, and we will do research with impurities. To be honest, there are also plans at SINTEF and at DNV in the Netherlands to build facilities. But again, to my knowledge, they are working on that, but they are not yet at the stage of you know, having the funding to build it. So that's, I hope, give you the landscape. So the next question is, I've tried to put some of the rationale here, but the next question to me is, can we calibrate with an alternative fluid instead of having a CO2 facility? And the reason is, obviously, as I was showing, there is a lack of calibration facilities around the world, especially for liquid and dense phase. The existing ones are restricted in operating conditions like sizes, maximum flow rate, pressure and temperature sometimes. And there will always be a degree of, you know, transferability. We can't match exactly all the single operating conditions around the world, especially the concentration and impurities. So that will be very expensive and time consuming to calibrate each single meter exactly at their operating condition. The other point is there are a lot of water and oil calibration facilities around the world. They are accredited, they are very well established, very low uncertainty, and the same for natural gas and nitrogen. Third point, and in this case, I'm focusing on Coriolis meter. The transferability of calibration for Coriolis meter has been proved for several fluids for oil and gas application. So I put a paper here, recent paper published at the Global, presented at Global Flow Measurement Workshop. One of the co-authors was my colleague Chris Mills. I think it's a very good paper, so if you are interested, it goes into the detail of calibrating Coriolis meter with alternative fluids. So the question really now I'm trying to touch upon is, can we calibrate a Coriolis meter with an alternative fluid and use it with CO2? What the test results tell us. So let's start with test results in gaseous phase. And you will see I'm always starting small scale and moving to larger scale. And in this case, we are starting from a Coriolis inch, which is a 1/4 inch in size. And that was tested at Idiot-Watt University as part of a PhD collaboration between NEL and Idiot-Watt. So the credit here for all this nice and great work goes to the PhD student, Johnson Jimba. And we have also tested at NEL, that's on the right-hand side. So the left-hand side is the benchtop facility at Idiot-Watt University. It's a benchtop facility, small scale, but is pretty unique because we use a primary gravimetric standard, so pretty accurate stuff there. And on the right-hand side is our low-flow facility at NEL. And these are the results for both facilities. So on the y-axis, the error of the Coriolis, on x-axis, max flow rate. Starting from the orange open mark, which are the nitrogen results at NEL. Then we move to the orange square at Idiot-Watt University. You can see both facilities agree pretty well in nitrogen, and that's a good result. We have two independent facilities agreeing. And then we have the green mark, which is gaseous pure CO2. and is bang on the nitrogen results. Very good results indeed. And everything more or less is within plus or minus 0.25% error band, other than the low end, which is expected for this kind of meter. So just putting this in perspective on the EU or UK emission trading scheme requirement of 2.5%, we see that we are well within it. But we need to be careful here, because the 2.5% is on pure mass of CO2, while the Coriolis will measure the bulk flow. So we need to account also for the composition analysis uncertainty. So we need to be careful, but we are well within it. And you may say, well, that was pure CO2. We don't have pure CO2. What's happening when we put impurities? Some mixers were tested by Johnson, and although they are not representative again of all the mixers are there, the results looks good and still in line with the pure CO2. So that's the first nice results. The second one is some tests that we recently completed at NEL. In our gas CO2 facility. We have tested, you can see 4 meters, but I'm going, so a turbine orifice, Coriolis and ultrasonic, but I'm going just to show you the Coriolis results. So we tested again in nitrogen in this case, and with pure CO2 is a 3-inch Coriolis meter, and you can see again within plus or minus 0.25 other than the low end, and CO2 and nitrogen agree pretty well. So let's tell a similar story. Again, in perspective of the 2.5%, well within it. So also look at what is out there. A very good paper from DNV, I think, yeah, 2021. You have the reference there, so you can read it. I recommend that. So they have tested again different meters, and in this case, I'm showing the result for a 2-inch and a 3-inch Coriolis, tested with natural gas and with CO2 at 95% and 99% concentration, different pressures, and again within plus or minus 0.25. And the Coriolis was previously calibrated, if I'm not wrong, at the manufacturer factory in water. So the transferability of calibration seems to hold also in this case. Another lab, Fortis BC in Canada, and this is a 2022 paper. You have the reference there, again from the Global Flow Measurement Workshop. Similar story. Calibrated with water is the black dot, with natural gas and with CO2, and results are still good. And if I'm not wrong, again, this was calibrated initially with water, and it's, I think, a 6 to 8-inch Coriolis. I think it's a 6-inch Coriolis, but you can check in the paper. So first bit of conclusion. We have 4 different labs, different scales, but similar results. So to me, that seems a piece of evidence started to appear. And these results suggest that a Coriolis meter can be calibrated with alternative fluid and used with gaseous CO2. Moving to liquid and dense phase, and we have done some testing there as well. And again, at Idiot University with pure CO2 in this case, you have the graph there. And we have tested with different pressure and most importantly, with different temperature. So you have 22 degree and you have 34 degree. 34 degree are the red triangle. Again, error on the y-axis and mass flow rate on the x-axis. And it's still the same 1/4 of an inch Coriolis. So good results, to be honest. one thing to flag is the shift that you can see we have observed when we move from 22 degree to 34 degree. And we're still investigating that shift. If it's actually related to the Coriolis itself, it's maybe an artifact of the test. So further research is needed here. But you may say, well, why is important 34 degree? Are we operating 34 degree? Potentially, if we are downstream of the compressor and close proximity. So potentially there we can have a bit of higher temperature than just the ambient temperature. And I'm aware that there are projects that are also operating at 60 and 80 degree, if I'm not wrong. So if this shift is true and does need to be assessed, yeah, we need to include that in our thinking. So luckily, we ERIC University and ANIA were able to recently secure some other funding, IDRIC Flexible Fund Round 4, to conduct some further research in this shift. Yeah, but also plot there on the right-hand side the phase diagram for pure CO2. And you can see that the red triangle, which is the 34 degree, is pretty well in proximity of the Widom line, which is the region where we have large gradient of fluid properties like density, for example. So we need to be very careful to operate in that area. And but it's also very interesting to look at what's happening there from a scientific point of view. So hopefully nice results and ahead of us. Again, put this in perspective of the 2.5%, just to give the feeling on where we are. Otherwise, the scale is important, and we are well within. And again, what about impurities? Mixture were tested by PhD student Johnson at ERIC University, and again, we are, we have a consistent behavior there. And I put also some of the output regarding this work that you can find in the open literature here. Then we move to slightly larger scale. As I was saying, we started from small, we go to large. So in this case, we have tested 5 different flow meters technology at the Institute for Energy Technology in Norway. So from right to left, a 2-inch orifice, at a 2-inch ultrasonic clamp-on meter, a 2-inch liquid turbine, and a 1-inch Coriolis. And to be honest, they all did very well. And I was particularly, surprised myself by the clamp-on ultrasonic, and that did very good result above my expectations, to be honest. So yeah, that was a very, very good and nice surprise. But we will concentrate on the Coriolis here and for this talk. So one thing to point out is there are no primary standard or traceability at IFE lab. So we needed to come up with how do we figure it out which is the true flow rate in that pipe. So in that case, we can't do an absolute, let's say, comparison. What we did is a relative comparison between the 5 different metering technologies. And for this work, we took as the reference value, the true value, the value from the orifice meter. And obviously, we calibrated the orifice meter, we assessed the performance, we have run an uncertainty budget. So we have done all that checks and homework necessarily to give confidence that is a good value out of it. And we have tested different conditions. So you can see 4 conditions here of pressure and temperature, and plotting against the phase diagram for pure CO2. We start at -20 degrees, so close to shipping condition, and go up to 40 degrees Celsius. And pressure between 25 bar and 90 bar. And these are the results which were presented and published by my colleague Russell Brown at the Global Flow Measurement Workshop in November this year, October actually, sorry. And on the left, you can see the results. Y-axis this time is the relative discrepancy between the Coriolis and the orifice. So it's a relative discrepancy there. Let's have a look at the results. So let's start with the square marks. So the square marks are the difference between the orifice and the Coriolis when we tested in oil, the brown marks, and in water with the blue marks. So you can see that in water and in oil, where we tested in our facilities in water and in oil, the 2 meters agree pretty well. We are below 0.1%. So it means they're reading the same or close to. And there you have all the other marks, the triangles, which are with CO2 at IFE. The results are not bad. You know, we are close to the 0.25%, but we can see a shift between water and CO2 in this case. And we have done further analysis, and we will publish all our results and thinking in a journal paper, also with the result for the other flow meters. But one point to notice here is that we are using the orifice as a reference, right? And the orifice itself has an uncertainty. So the orifice itself is not spot on. So this discrepancy between the two in CO2 might be due to the orifice and to how the orifice operates with CO2. And that's I will clarify that better. We will clarify better in the journal paper. Again, the 2.5% perspective, and just to conclude on this case, that early experiments suggest that, yeah, well, if I go back, yes, we are still well within the 2.5%, right? If you look at that. So early experiments suggest that Coriolis meter could be calibrated with water used with liquid dense phase CO2, but I really stress that we need further research for that. And this is part of our future plans. So we are partnering with 20+ partners, organization around Europe, in a project called ENCASE. And as part of that, we will do, there are a lot of working packages. It's not just flow. There are question of state and pumps and investigation of their performance, modeling of the network, and so on. But for flow measurement, one of the activities is for us, for NEL, to build the liquid and dense phase primary standard facility that I was mentioning before, and do the research with including impurity. And we will also do research on sampling and analyzer system, how do they perform, and on density measurement. But we are also at other plans, like we will going back to IFE next year and do further research there in dense and liquid phase with a different meter and with extended condition. As Yessica was mentioned, we are both part of MET CCUS, another big European project, and that we are developing primary standard for gas, do further research for gas. Also, fluid properties, we have developed a fluid properties lab at NEL, and so there are colleagues of mine at NEL that are expert on CCUS, equation of state and fluid properties, so they're doing a lot of nice work in that area, especially on impurities, and gathering experimental results from impurities and validate equation of state. And obviously keep on collaborating with Utrecht University and do some further tests there. And ultimately, our really purpose is to share knowledge, yeah? To create that body of knowledge and to share that. So that's, we will publish report, we will publish journal paper on the gas and liquid dense phase test. And we have also recently completed the draft of a very, very comprehensive literature review and you know, assessment on flow and compositional measurement technologies, and that's the manuscript that you see on the last one on the right. It's called Towards Standardization Measurement of the CO2 Transfer Across the CCS Chain. So we are in the process of submitting that. Hopefully we will be lucky, And the idea behind this piece of work is to start creating that framework for standardization. So the idea is to provide a first piece of work which provide a knowledge base for standardization in this area, because ultimately, as I was saying, that's what we are aiming at, to have a standardized operation, to have best practice guide in place, and to support industry in scaling up CCS. And that's all from my side. And so watch this space, and we will make all this stuff available to the public. And you're always welcome to contact me if you need to. So that's me, and yeah, I'll go back to you, Lorenza.
Yes, thank you, Gabriele, very much for your presentation. I think I now invite both Gabriele and Yessica to come back with your cameras so we can start the Q&A session. We actually have a few questions in the chat. So the first one is for Yessica, sorry. I don't know which one is the correct pronunciation. Okay. So, hi Yessica, could you detail the source of the stated uncertainty tolerances plus or minus 1% for liquid and plus or minus 0.5% leakage? These do not correspond to the plus or minus 2.5% legislated for CO2 transfer to storage under the EU ETS directives.
Yes, you are very, very right. That's why I said it was the most strict legislation or regulation that we have in place. Yes, correct. 2.5% is what is legislated under the ETS. The 1% I claimed is coming from the European Measurement MID, Measurement Instrument Directive, I think is the name. That claims 1.5% for the entire system and 1% for the meter. There are other legislations like the OIMLR 117, which claims it should be 1.5% also. So I didn't want to go. It was my intention to go into like the legislation part of things. So that's the strictest ones. That's why I quoted it. And the 0.5%, like I said, is not a regulation. It is the EU taxonomy establishes that for an activity to be sustainable, the transport part, the entire transport part, should not have leaks more than 0.5% in the mass transported. So that's where they are coming from.
Okay, that was very clear. Thank you. We have a second question for you. So also thank you very much for your interesting presentation. Apart from measurement accuracy, what about the most critical issues to improve model reliability? How models are calibrated and validated?
Yes, well, models is a world on their own, and there's different, it depends on what type of models we're talking about. If you're talking about equations of states, for example, they're usually calibrated. Well, the equations of state that we use right now, the Span-Wagner, for example, is it's based on data. A correlation type of equation of state is based on data. So it is. Sorry, I have an incoming call, and it's just Sorry, it's yes. So that's how it is calibrated with experimental data. There are the most critical points, if you ask me, I think has to do with reactive measures. Once you have, because these equations of states are coming from vapor-liquid equilibrium. So once you have a second phase and that phase reacts and creates other components, I don't think that has been sufficiently studied yet. And there's also issues with what is called second derivative or second order derivatives from the equations of states, which are not coming from the VLE data, but is it's like a level down, which has to do with like speed of sound, for example, which is relevant for ultrasonic meters, or heat capacity or Joule Thomson, which is relevant for the pressurization and safety in CCS. So I hope that answers the question, but modeling is a world on their own, so it's a bit difficult to know what model. Yeah.
Very complicated. On the chat, there's also a question for Gabriele. The presented results are very interesting and promising. What about TRL, so the technology readiness levels of CO2 colorimeters? Are the instruments or measuring methods, materials, and so on directly derived from high TRL natural gas systems?
Yes, this is a very good question, because we can do a lot of nice testing, but if the technology is not available to industry, then we need to wait years to be deployed. You know, that's we need to scratch our head. But as far as I know, Coriolis meter are out there. There are a lot of well, very well established names in the industry that can provide Coriolis meter. We can buy them. They're available on industry, you know, and they're up for the job in terms of material, in terms of capabilities and everything. So as far as I know, there's no such a problem for Coriolis meter. They are readily available, and yes, and they have been, yeah, they've been derived and developed for oil and gas application in the past. But as far as I know, but you know, I'm not a manufacturer myself, but as far as I know, they are capable 100% to deal with the condition encountered in the CCS chain. Yeah.
Yeah. There's another question again. Hi, Gabriele. Could you comment on the use of fixed volume provers for calibration of meters on CO2 phases in situ as compared to laboratory flow calibration?
Yes. Okay. Yes. That's another good question, because calibration strategies might vary, you know, and the main driver for the calibration strategy is about financial exposure. So we can spend a lot of money and also have you know, more complex and time-consuming calibration strategy, but they are only justified if there is a need for that, either from a regulatory purpose or for you know, financial purposes. So in terms of CCS, most probably we may have you know, a duty meter and a standby meter, and then we take one of them out and send to a lab, or we can have a master meter on the skid, and actually we calibrate the duty meter against the master meter, and the master meter we send to the lab. So that's the two probably, given the high uncertainty figure we are quoting, and given the current price of CO2, that probably the one you know, industry we will look at. But yeah, it's correct. There is a third one, which is calibrating with a prover in situ. So either with a portable prover from a third-party company that come there and install the prover and calibrate your meter, or with a fixed prover that is installed within the measurement system with the metering skid. That probably might improve the uncertainty. And when I say probably, it's just we need to look at that, because a prover is a volumetric device. And what we want is the mass of CO2. So, and what is in the middle is the density, as Yessica was saying. And density for pure CO2 is not a problem. And density for CO2 with impurities, we still need to think about it, especially if we use equation of state. So yes, piston prover is an option. Personally, I don't think is probably the option at the minute, but yeah, buy is an option of the table if you know, if the industry is looking at it. But we will need consideration on density there, and also on other stuff like compressibility effect of the prover, and you know, other consideration that need to take place. Sorry if it took long, but it's a difficult question, and I can expand more if needed be.
Yeah, but we still have one more question. Does high volume flow measurement is required in calibrating CO2 metering technologies in gas, dense, and liquid phase to meet CCS industry needs, in particular to assure costly transfer credit checks? I think this might be for Yessica or for both of you. It's not specified.
I'm trying to interpret what high volume flow measurement. I assume high flow rate.
Yeah, guess so.
Yeah, high flow rate. Yes. Jessica, I don't know if do you want me to step in?
Yes, please. I think this is more into your
well, it depends where you are in the CCS chain. So if you are in the truck lines, for example, for onshore, offshore transportation, so where we have the different emitters in the network, that coming flow that goes into a big trunk line, yes, you can have multi-million of ton per annum. So probably you start with one and you can go up to several of them. So in that case, you need high volume there, high flow rates. Potentially 1 meter might not suffice in that case. You may need to multiple meter in parallel. At the emitter side, so between the capture plant and the transportation network, the flow rate really depends how big is the emitter. You may have big emitter, for example, a big coal plant. You can have also smaller emitter. So it really depends how big is the emitter and the volume that they capture. So in that case, it can fluctuate. I think. Yeah. I don't know. Just you have to add.
Yeah, completely right. I think another perspective is that we still don't know if we will need to calibrate with CO2, and this is what Gabriele's presentation was. Why it's important to understand the transferability between water and CO2. So I don't know if that's where the question was also stemming from, if it's actually the flow rates with CO2, but for sure when you are calibrating, you need to do it at the flow rates at which, or at least encompassing the flow rates at which you will be operating.
Yes, thank you very much for your answers. So far there's no more questions, and it's over 3 o'clock. So if you don't want to add anything else, I think we can stop the meeting here. So thank you very much, Gabriele and Yessica, for your very interesting and engaging presentations. I also would like to thank OGS for organizing this webinar and remind you that next week there's the next webinar, so on Wednesday, the 29th at the same time. So thank you very much.
Thank you all.
Have a nice evening, everyone.
Yes, you too. Thank you.
Bye.
Bye.